All right, let's have a look at this series. So, okay. Sigma n equals 1 to infinity of e to the negative n squared. So, like I mentioned before, it would be a good idea to write that negative into positive. That is 1 over e to the n squared. Oops. So from here we need to come up with something simpler. Well, something simpler than this could be like, okay, to compare with. Sigma n equals 1 to infinity, 1 over e to the n. All right. Why am I coming up with this new series? Well, so think of 1 over e to the n squared. Where is 1 over e to the n's we're going to go for large values anyway? So, is this quantity going to get really big, or what's going to happen to this quantity for large values of n? It's going to get really small, all the way to 0, right? So that sounds like convergence, all right? And well, because this is not going to go to infinity, this is not going to diverge, well, then we can come up with something that looks similar and simpler, which also happens to diverge. Right now, the format right here may not be the best to determine the convergence or divergence, so I would rewrite this series as 1 over e to the n, and this looks like the geometric series with r equals to 1 over e. Well, we know the value of 1 over e, well, the value of e is 2.71, 81, whatever number of decimals. Well, the reciprocal of that number for sure has to be less than 1, right? So that means here we have a convergent geometric series. Okay, so we have a geometric series. Well, in this case, that means that we need to show that tiny is less than or equal to small, where the tiny is our problem, that is 1 over e to the n squared, and the small one is 1 over e to the n. Is that inequality true? It is, because in the denominator of the left-hand side of the inequality, we are raising the exponential to a larger number because of the squared on the exponent. And of course, dividing by a larger number is going to make it smaller, and that inequality true. This means this is enough argument to say that the series converges by direct comparison test. All right. Okay, of course, what could go wrong about this test? Let's consider the series that we have here for letter D. Okay, so sigma n equals 1 to infinity of 1 over the square root of n plus 4. Well, number one, let's see if we can compare this with a simpler series. So compare with it's a p-series, isn't it? It's going to be sigma n equals 1 to infinity of 1 over the square root of n, which is sigma n equals 1 to infinity of 1 over n to the 1/2. Alright? And in this case, what are we going to have? It's a divergent p-series to compare it with. Alright, so for divergence, we need to show that huge is greater than or equal to big. Okay? That's what we need to show. Well, so again, the huge will be the original problem, and the big the test. And let's put them together. And is 1 over the square root of n plus 4, is that greater than or equal 1 over the square root of n? No, right? So on an example that we did before for divergence, we have a minus in the denominator, making it making the quantity smaller, and therefore making it a larger number overall. But in this case, we cannot show that huge is greater than big. So in this case, test inconclusive. Test inconclusive. So we need a plan B in this case. So the plan B right here will be to use the limit comparison test. All right. So, and again, same idea. We're going to have a complicated an ugly looking series, and we need to obtain a simpler looking series that we can use to compare it with. But in this case, we're going to find the ratio of these two quantities. All right. Again, as usual, just like before, this is the problem series. And this is the test series. All right, just the same way as in the direct comparison test. So let's determine whether each series converges or diverges. So let's, okay. Before let me explain the test. Well, so what we're going to do, we're going to find the limit of the quotient between the expression in the problem series to the expression on the test series. And if the limit is a positive value and also a finite value, then our original series will do whatever the test series does in a similar way than the comparison. But in this case, instead of comparing by means of an inequality, huge greater than big or tiny less than small, we are looking at a limit value, and as long as it's positive and finite, and then we're good. Okay. If the limit is, say, d and e or infinity, well, then test inconclusive. We need to find another way. All right. So let's determine whether each series converges or diverges. So let's see. Let's compare with sigma n equals 1 to infinity, 1 over 2 to the n. All right. Okay, don't write this down. So what do we have first of all? Well, yeah, that's fine. We need to write this. Okay. This looks like n equals 1 to infinity, 1/2 to the n power. And in this case, well, we've seen this form of a series before already a few times. This is supposed to be a convergent geometric. Alright, if we were to do it by the direct comparison test, and this you don't need to write this down, then we would need to show that tiny is less than or equal to small. Alright, now is 1 over 2 to the n minus 1 less than or equal 1 over 2 to the n? No, right? The test would fail. So in this case, we're going to use the limit comparison test instead in order to, as a way around this issue here. So, nope, not direct comparison. Direct comparison failed. Let's set up a limit comparison then. All right, so for the limit comparison, we need to set limit of a sub n over b sub n as n approaches infinity. And our a sub n, again, it's the expression in our original problem. In this case, 1 over 2 to the n minus 1 divided by 1 over 2 to the n as n approaches infinity. Well, let's simplify this complex fraction by multiplying by the reciprocal of the denominator, which in this case is limit 1 over 2 to the n minus 1 and approaches infinity, and times 2 to the n, alright, over 1. But in this case, how about, let me write down that 2 to the n in the numerator, alright? Well, of course, there's a couple of ways to, to evaluate this limit. Number one, you can divide every single term by the highest degree or the highest order term. Or, well, you have basically times invisible 1 times invisible 1. Even if we did the L'Hopital's rule at least once, we would end up with this 1 over 1. So the limit right here will be equal to 1. Now, what about this number? The number 1, is this a positive value? Yes. Is this finite? Yes. We're good then. Positive and finite. Therefore, the original series will do exactly what the test series does, which in this case is to converge. Series converges by limit comparison test. That is LCT. We can abbreviate by using LCT. Alright? Let's use the limit comparison test on the next example. B, okay, sigma n equals 1 to infinity of 7 to the n over 3 to the n plus 9n minus 3. And we already did the test series for this at the beginning of the section when we covered the overview about what the comparison tests are about. And let's just use that information to compare it with sigma n equals 1 to infinity. That's 7 to the n over 3 to the n, which is 7/3 to the n. And what can we say about 7/3 to the n? Diverges. By which test? Geometric. So we have a divergent geometric series. So we're going to set a limit again. The limit a sub n over b sub n as n approaches infinity. That is the quotient of the expression in the problem series divided to the expression on the test series. And well, this will be, yes, it's going to look a little bit big and approaches infinity. So that's 3 to the n plus 9 n minus 3, all under 7 to the n. The whole thing divided by the test series, which in this case 7 to the n over 3 to the n. Alright, let's talk about this limit. Of course, again, keep in mind that this is divided by 7 to the n over 3 to the n, so all we do is multiply by the reciprocal of the denominator. So limit n approaches infinity, that's 7 to the n over 3 to the n plus 9n minus 3 times 3 to the n over 7 to the n. And the good thing here is these 7 to the n's get cancelled. Actually, And we're going to get a limit very similar to the previous one. So limit n approaches infinity, 3 to the n over 3 to the n plus 9 to the minus 3. And well, I mean, 3 to the n in the numerator, 3 to the n in the denominator, very similar to the previous limit. The invisible coefficients are 1 over 1, if we will. So final answer to this limit, which is also positive and finite, because that's the nature of the final answer in the limit. Then the original series will do whatever the new series does. In this case, diverges by limit comparison test. All right. Question?
Say, is it possible that you could get, even if you did the LCT and you get like a negative value or infinite, would it be inconclusive or something, or does
it's possible to get an inconclusive. Okay. If you get an infinity or a negative value. So, so the requisite for the test to work is that our limit is positive and finite. All right. Whatever big number, even a decimal, rational, irrational, it doesn't matter. So, as long as it's positive and finite. And